The recording will be posted here, youtube.generativeai on aws.com, or you could just search for this on YouTube. Today we have a super exciting lineup, not just an exciting lineup, but a super exciting. We've got Multimodal RAG with the open source project called Milvus, and this is by our good developer advocate friend, Christy Bergman, who is at Zilliz. So hi, Christy. Thanks for joining.
Hello.
And then co-author of our book, Shelby Eigenbrode. So she'll be speaking. She's with AWS. And then I'll be speaking on multi-agent and multi-prompt and basically pipeline like optimizations with a cool project called DSPy. If you have been calling it DSPy or DSPy, you are incorrect. According to the creator of the project, it is DSPy. So I'll talk about the history of that and kind of what the core fundamentals are of that project, and hopefully show a demo that I'm scrambling to get working here in a bit. So I guess, yeah, Antje, do you have anything else? Do we know what we're talking about next month? Antje, do you remember?
I think we're talking about more multimodal stuff.
Gotcha. So, so Shelby, that was one of the big section or the big chapters that you wrote, Shelby. So probably have you back. And okay, Christy Bergman, take it away.
All right, let me share my screen.
Yeah, and I'll go off camera and I will mute.
Where did my screen go? There we go. All right. Okay, so hopefully everybody can see my screen. So yeah, so this is going to be a very quick talk and demo of multimodal RAG using Milvus, open source vector database, Unum, very tiny clip embeddings, and GPT-4o. And so as Chris said, I'm a developer advocate at Zilliz. It's a company of maintainers of the open source vector database Milvus. And this is also my LinkedIn if you'd like to follow or connect with me. So just a quick introduction to the company. You can think of open source, you can think of vector databases either open source or closed source. There are a lot of different open source databases. One of the nice things about our project, which was donated to the Linux Foundation, is if, for example, you're coding in Python and you don't specify a vector index, it'll default to the system index, which in the open source auto index defaults to HNSW. And if you were running that on Zilliz Cloud, then it would default to a proprietary faster index. Quick overview, what I'm going to talk about today, quick introduction to RAG, and then talk about some multimodal embedding models, and then demo multimodal RAG. So yeah, just as much as this month, I was able to go to Gemini and I'd ask, list 3 politicians born in New York, and one of them would be Hillary Clinton. But if you go to Wikipedia, you can see that she's actually born in Chicago. So that's a hallucination. Yeah, today I tried it and it says that they don't want to respond about elections of political figures anymore. But yeah, and quickly, why do models hallucinate? This is because the LLMs are trained on sequences of tokens. And so, for example, if you're trying to predict the chicken walked across, probably it's the road, but because of the data that the models have been trained on, there could be some random things that were snuck into the training data. Where do the embeddings come from? They come from the next to last layer of deep neural networks, and not the last layer, which is the softmax, typically like 0 to 9 for predicting a digit, but the next to last layer. And the reason is because of, you can think of these as like big FFXs, where X's are unstructured data inputs like text or images, and the F is the transformation of the deep neural network itself into a Y, which is a vector. And so that those next to last layers of trained weights people have learned just contain all of the knowledge of that model. And so these vectors are stored in a vector database and searched. Which brings us to retrieval augmented generation. The pattern is you take your data, or more recent data or something that might not be out there available on the internet. You use inference, an inference embedding model to transform the f of x's, which is your data, chunks into y's, the vectors, put them in a vector database. That becomes your knowledge base. And then you might deploy this application and a user comes along, asks the question. There is a very fast, because at this point, cosine distances of vectors is a very fast calculation to find the closest chunk that answers that question. The question and the retrieved chunk are stuffed into the context and sent to the generative LLM model, or what we just call LLMs, and hopefully what comes out is a more reliable answer. Oops. All right, which brings us to the embedding models themselves, which deserve a little bit deeper look. So in the original 2017 paper, transformers had two sides, the encoder and the decoder. And what researchers have learned is that you don't need both sides, actually. It's you can separate them. And what the encoder parts have turned into are modern embedding models, and the decoder parts have turned into what we know as the GPT-4s, for example. And just to highlight what workhorses these embedding models are, if you go to Hugging Face and look at, for example, BGE large EN, you can see that it's downloaded in the last month more than 1 million times. And if you look at even Llama 3 70B Instruct, it's a 500,000. How did we get here? Basically, I don't want to go too deep into this, but most text embedding models are based on SBERT architecture, where sentences are trained, or sequences of tokens are trained, and then they're combined using cosine similarity pooling. Vision transformers, originally this one came out in 2021 from Google. So the image is like chunked into chunks, and then they used to be trained using CNNs, but then along came the vision transformer, which uses patches to transform them and then feeds them into a regular transformer encoder. And so what happened is, beginning with OpenAI's model, then the embedding, these multimodal embedding models now take any kind of input, such as text or images or even videos now, and outputs them into the same vector space, which means that when you search, you can search using text and you might retrieve an image or a video, or vice versa, you might search with an image and retrieve text. Just high level, the way these fusion models are organized, there's late, mid, and early. So the most common models are late fusion, such as the OpenAI Clip, which came out in 2021. Most of these still have only text and image. So like there's so basically late fusion, you have two towers of transformers. So you can think of them as the separate encoding models, one for text and one for image. And then they are a contrastive loss is applied per tower to fuse the models together into the same embedding space. Mid-fusion is where the fusion is happening just a little bit earlier. So again, you've got the two towers of models, for example, the text encoder and the image encoder separate, and then the contrastive learning per tower is fused in a separate multimodal model. For some reason, my cursor isn't working. Okay, and then the early fusion is the holy grail of multimodal embedding models, where things are headed. Today, there is Meta's Chameleon model, but it still only has two modes, text and image. And right now, the main model that has many different modalities is this Meta Image Bind. Which brings us to RAG. With multimodal, now we can not just input text, but we can also input many different kinds of modalities to to augment the information sent to LLM. So my quick demo, today I'm going to use these from these very small embedding models from Unum. Okay, I think I can move around. Oh, there's my cursor. Just gonna move this. Let's see. So yeah, there's Expert, there's Vision Transformer, there's OpenAI's based on Vision Transformers. Here is Unum, which is available on Hugging Force and Hugging Face, and you can see that it is based on the Vision Transformer model with BERT. It supports 21 different languages, and its dimensions are 256. So I'm using it because I have the poor person's laptop at 16 gigabytes RAM, M2, and I needed a very tiny model that I could download the weights locally and run. So I'm going to jump straight to my notebook now. And let's see, maybe I need to make this bigger. Can everybody see this?
Yeah, looks good.
Okay, great. So I can quickly run this guy. So basically I take all this data, a data set, it's 25,000 images, and load a mapping CSV file, which tells me which photo ID, which image URL, etc. I'm going to create a collection, and this is the few important parts to notice here. There's once we're doing multimodal RAG, you need a vector database that's capable of hybrid search. So, for example, when I create this database, I'm going to, I need to specify the embedding dimension, and then I need to specify a vector, an image vector and a text vector, for example. And then when I create this, I also need to, yeah, I'm going to have to be able to search both vectors, this image vector and the text vector. And I need to specify an index for both of them. I'm going to use the auto index, which I mentioned, and just the cosine distance. So now I'm going to download that clip-based late fusion model from Unum. Going to run it, and because I'm running on a very small laptop, I've only got, I'm going to use batch size 10, and I'm only going to be able to encode 100 of these for this quick demo. And you can see when I loop through it, encoding the images 10 at a time. I'm going to have an average embedding time of 5 seconds, but the insert time is 0.03 seconds. So that is something that a lot of people don't realize, is it's really the embedding time that's taking the most time here. Okay, now I'm going to define, okay, now I'm ready for search, because I've inserted all these images and text into the vector database, and now I can ask different questions. So for example, if I translate the first question about brown leaves into French, and I do a reverse image search. Oops. Oh, I picked an image of a cat as well. But first I'm going to just do a reverse text search, text to image. So I'm going to say the brown leaves, ask it to retrieve images of brown leaves. And with using that query, brune pendant la journée, I get some pretty good images. Actually, I've noticed the text image is the most accurate for most of these multimodal demos. And I've only got 100 images here, so I'm not going to get a perfect match every time. Now I'm going to do the reverse image search of the cat. So I take my cat using this picture, and maybe I want to find other pictures of my cat because I have so many pictures maybe. So yeah, pick another picture. I can also say, for example, that I want to look for Rocky Mountains at the golden hour, and I can have both text and an image. And in this case, I chose Arabic because, yeah, it is a very commonly spoken language besides English. And I'll pass as well this image, and passing both into my multimodal search. I will get pictures of mountains at sunset. This last one's not a good match, but the other ones were. And I don't know, I don't think I have time to dive in too much into exactly exactly how, yeah, this is what the indexes look like when I specify them for image and search. And this is not meant to be a demo of GPT-4o, but now I could take, for example, text and images, send them to GPT-4o with a short prompt like, output this blog in Hindi, generate this blog in HTML, send this to GPT-4o using our standard OpenAI API, and I get an error. Let's see, what did I do? Okay. I will have to fix this later. But what I did
think
is,
it's
what it did is it generated
unsupported country. Yeah.
unsupported country. Oh,
Mhm.
oh, oh, this is because I'm on a this is because I'm playing around with my VPN. Oh, I see what happened. Okay. Yeah, I'm playing around with my VPN and I see I'm running out of time. But basically what I did is I generated a blog in Hindi, and then I should be able to go over here and get my website. And it did generate a blog in Hindi. But the reason I'm on my VPN is because as I mentioned, with those embeddings take a lot of time. So here's an example where I've embedded 3,000 images. And so I have more images. And because this is an AWS talk, I will show just briefly. I'm using Ray. I need to have a Ray cluster up and running on EC2s. I need to have some data in an S3 bucket, and I can take a look at my Ray dashboard. And so what I did is I just ran the using Ray data. I ran my embedding inference with a lot more images, and now I can browse for bigger files. So for example, I can take a cat again, and I can say headphones. And what I've done is I've taken actually an AWS data set. So this is all AWS products or Amazon products that are sold on the marketplace. And it's going to search 3,000 images that have been uploaded. And make sure my VPN is still working. Oh, it's running still. All right, beauty of live demos. Okay, so I've got a bunch of images, and now I can send all of these images to GPT and ask GPT which of these images are the best. And GPT-4o, because it has multimodal capabilities, should be able to pick out the best of these 20 images that we sent it, which one is the best answer to my original image and my request, and it picked out these cat earphones. So yeah, that's a very quick demo. I know I skimmed over a lot of theory and a lot of details, but hopefully you get the idea there that you can, you need these multimodal embedding models is the key. Then you can do multimodal RAG using the LLMs, which are now multimodal, especially with GPT-4o. And the embedding step takes the longest, but you can shorten that by using Ray data, for example. Right.
Cool. Great stuff. Okay, we have a ton of questions. Maybe we'll take just like one or two here. So
Yeah, I can make
people
the
are,
notebooks public. The
yeah,
the notebooks are on my GitHub, as well as there's a GitHub here called Milvus Bootcamp, which is where I put stuff.
Gotcha. Can you paste that into the thing here when you get a
Sure.
chance?
Yeah, actually, I've got it all here. Oops, not this one.
And I guess I'm just skimming through all the questions here. How are the distances calculated when
Yeah.
you combine the text and the image? Just sort of at a high level.
Yeah, so that I kind of skimmed over that in my slides. That is the fusion step where you take those two separate models, the text embedding model and a image embedding model, and then you fuse them together using cross entropy loss. And where's my slides go? Oops. Nope. Oh, I seem to have lost my slides. Oh, where'd my slides go? Oh, I might have, maybe I dismissed them by accident. Yeah. So basically, when I was talking about this, where you've got the two towers of text and image encoders, and then they're fused together into the same embedding space.
Gotcha. Okay. And then someone's asking, how is it possible that a query posed in a different language can retrieve the same image or the correct image?
Yeah, good question. So these models are getting to be, besides English, besides being trained on English language, they're being trained on many different languages, which is really the heavy lifting, I think, is in these embedding models. But they're being trained on multiple different languages as well as images. And the key, especially with CLIP, came when they took this vision transformer architecture and they added, let's see, do I have a picture of it? They added oops. They So it used to be with vision transformers that there was a kind of like a cat classification, such as bird calls, for example, and you're training the vision encoders to understand and classify images. So OpenAI took the extra step of training with text and image at the same time, so that you instead of having classification of fixed classifications, now you have the text that came with the image itself as kind of like the target classification. And if you go to Unum's page here on Hugging Face, you can see the different languages it was trained on, and you can also see their evaluations where they showed that with embedding models, when you see this at 1, at 5, that means top K was 1 or top K was 5. And when you have top K larger, I think they wanted to point out that they're beating OpenClip a lot of times, especially for some of the lesser known languages. Like, for example, Hebrew is a hard language to train on because there's not as much data out there. So yeah, in a nutshell, that's how it happens.
Okay, and there was an interesting question about 3D images or 3D, and it kind of reminded me of, at some point, this applies to video as well too, right? Which is a bunch of images and a time factor. So yeah, any comments on how this could be done with 3D or with video?
Yes, there is a model that's got, I think it's called Image Bind by Meta. And it has no, it's the best one to go to. It does have, in addition to it's got depth and heat maps as well as text and images. So there are some, it's one of the few out there right now that has this extra, that I know of at least. There's probably more. If you go to Hugging Face, there are so many different embedding models and LLMs to choose from these days. It's really amazing. One of the speakers at one of my unstructured data events said we're living in the golden age of Gen AI. So really enjoy it. There's so much innovation going on. But yeah, I think this is one example to take a look at. And this is where at least for me, I could not run this on my laptop. I needed to run it using Ray Data for the embeddings because it was just too big.
Gotcha. And oh yeah, actually, fun question. Someone asked how you got the UI to run using Ray. Is that using? It's not really using Ray, is it?
How did I get the UI to run?
Using the Ray framework might be.
I think, yeah, I think this is definitely a good place to go. And I was a little bit rusty. I used to work at Anyscale as a dev
Yeah,
advocate. So I used to do this all the time, but it had been a while. So I went and went here, and I just literally followed all the steps here where you do array up, and then you can get a local you can get a local um, access to the dashboard.
gotcha. Yeah, I think
Yeah.
there might have been confusion, or maybe I'm confused about the question, but it seemed like the UI that you were showing was
Yeah.
also being powered by Ray, like the sample demo UI, but that's just like a Flask app or something, I
Yeah.
assume,
So
right?
these would be just kind of separated tasks because when you go to the RAG, all right, I'm losing my pictures. Oops, I don't have my RAG image here. When you do RAG, there's the pre-step where you do the embeddings, and then once the embeddings are stored in the vector database, that's deployed as your knowledge base, and then that's where after that people can come in and ask questions. So the Ray part would come in as the pre-step, the embedding.
Gotcha.
It's kind of an offline task versus the online task of retrieval and search, which is super fast, is done live while the users are asking questions.
Gotcha. Yeah, and then Danny mentioned here in the comments that the web UI seems to be based on Streamlit, so which makes more sense.
Yeah, this
Okay,
was just yeah, and then I was just demoing a larger example where the embeddings were pre-calculated, pre-stored, and then I can deploy a little chat app using Streamlit.
and I think the intuition that I was trying to get at with my video and 3D question is everything comes down to a token. And in
Mhm.
language, we've become used to the idea of a token being a word or a partial word. In an image, and I think, like you mentioned this, Christy, they're patches. In
Mhm.
a three-dimensional world, because actually one of my customers is doing this, the 3D world, a patch is all three dimensions in space. And
Mhm.
I believe it's similar with video as well, where it's like the frames before and the frames after, and you can adjust what that concept of a token means, and then still goes through some of the transformer. And there's
Mhm.
and yeah, hopefully we'll get to this next month when we talk about multimodal in depth. But there's a newer algorithm that combines diffusers and transformers together that is pretty promising, and I believe that's what's being used by Sora and some of these video generation models.
Yes.
So
Yeah, so I saw a demo recently using image bind with video. And basically that's what they did is they took frames and passed them through image bind, which is also a clip-based model. I can't seem to find, maybe I put it in Scratch. I guess I put it, oh, darn. Okay, I can't find my slides anymore. I'll have to find those. Or I made a nice picture of what's going on with the vision transformer, but it's got some positional encoding in the architecture of the vision transformer.
Gotcha. Okay. I think someone's asking if the dimensions of the image matter when does the resolution of the images matter?
This I can't remember actually. I don't remember. I think they do have to be square. But I better look that up. Because
Right. Usually,
yeah,
I've seen them. Yes, go ahead.
Yeah, so there are data sets out there, and the ones that I used, for example, I used Unum's data set, which they put out there, which I believe there's probably some more detail in those data sets themselves of maybe some preparation that they did. And the other data set I used was Kingdom Cattle. It's an Amazon products data set. So maybe there's more. I would have to look in here to see if there's some explanation of what they did.
Yeah, so a couple of people confirmed that the image encoder will resize it.
Okay.
Okay. We are at the bottom of the hour, so I think we got to move on to the next talk. Christy, thank you so much. Great stuff. If there's any slides or anything that you can point folks to, that would be great as well.
Yes.
And also, we do cover some of this, and Shelby's coming up next, but she's not talking about multimodal today.
Yeah.
Somehow today, ended up being multimodal day. But we do cover this, I believe, in chapter. Shelby, do you remember which chapter is the multimodal? Is it 10 and 11?
10 and 11, yep.
Gotcha. Okay, so yeah, Christy, thanks so much. If you do need to take off, feel free to. Shelby, do you want to put on the video, grab the screen, and I will mute my video.
Yes. Sorry, working on my share here. Oh, no. That's not that one. Adobe Acrobat. All right, can everyone see my screen okay?
Yeah, if you can close the all tools thing maybe or something, and
Oh yeah,
zoom
get it
in,
bigger.
would be great. And Shelby's broadcasting from the mountains of Colorado, so we're lucky she even has internet.
I am indeed. So apologize if there's any delay. But yeah, so in chapter 8 we talk about a bunch of different model deployment optimizations, and with model deployment, model inference, it's pretty specialized, right? And largely because with inference so when you deploy a model and you're performing inference that model, right? There's two key phases in that inference. So there's a pre-fill phase. And with that, what we're doing is we're taking, basically it's processing the input tokens, and we're computing intermediate keys and values, right? That are used to generate the first new token. And because each of those new tokens depends on the previous tokens, it's a heavily parallelized matrix to matrix optimization, or matrix to matrix operation. And what that means is it results in heavy utilization of the GPUs that you're using to host. And then in the second phase, which is the decode phase, essentially in that phase, the LLM is generating output tokens auto-regressively one at a time until the stopping criteria is met. And each of those sequential outputs or output tokens basically needs to know all the previous iterations of the output state. So those key values that we talked about before. And because in this case, it's a matrix to vector or operation, it doesn't utilize as much GPU compute, right, compared to the pre-fill phase. So each of those phases alone can have optimization techniques applied to them. And then also just the pure size of these models bring inference challenges in terms of memory utilization and then the storage requirements to host these models. So like I mentioned before, optimizing these models is pretty specialized, or it can become a specialized task, looking at both model optimization techniques that aim to reduce the model size, which we go into a lot in this chapter that we'll talk about, and then also different model optimization techniques used for inference as well, right? So reducing the size of the model and then employing different model optimization techniques. One thing I did want to point out, and I'll post the link inside here. So we had our New York summit last week. And part of that summit, we did introduce, and this is on the SageMaker side, a model optimization toolkit, right? To allow you to essentially implement some of these model optimization techniques a little bit easier. So things like quantization, speculative decoding, a little bit easier for hosting. Oh, thank you. Chris posted it too. So we'll go through this chapter. In this chapter, we focus, well, in this section of the chapter, I would say, we focus a little bit more on the model optimization techniques that aim to reduce the size of the model, right? Because they are so large, they do require a lot of compute. A lot of these optimization techniques we're going to talk about right now, and we'll talk about it in not high-level detail, right? So we have time for Chris, but we'll talk about some of these techniques. But if we look at them, we have pruning. So pruning, essentially, we're looking at reducing the size of the model by removing model weights. So in this case, we're actually removing model weights, whether that's removing the layers of the model, entire layers, entire blocks, that sort of thing. So that results in a smaller model because we're actually eliminating the model weights. In the second case down there, quantization. Quantization has become a really popular technique, right? Because in this case, what we're doing is we're taking the model parameters and we're using a lower representation of those. So converting from 32-bit to 8-bit, or, in this example to 8-bit to quantize. So this is post-training quantization. So you can do quantization during training as well as post-training quantization. And we do cover training or quantization during training in, I can't remember the chapter, maybe I think it's 3. But this is specifically referring to post-training quantization. Let's see, LoRa, QLoRa. So the LoRa, QLoRa, right, those are quantization techniques during fine-tuning, right? So you can do quantization in training, which is training level quantization, and then post-training quantization. And then finally, we have distillation, right? Where in the case of distillation, what we're using is basically a teacher model. So a larger teacher model, in this case, typically looking at the large language model, generative model. And we're using that to train a smaller student model. And in this case, whereas with pruning, the weights change, and even with quantization, right? Because we're doing a lower representation of the model weights. In this case, the weights of the teacher model don't change, but we're using that to effectively train a smaller student model. So let me go talk about a little into each of these specific items. So like I mentioned before with pruning, and the thing to keep in mind, like with each of these different techniques, there is something to be considered and something to benchmark in terms of the trade-off in accuracy and performance, right? Or accuracy, performance, as well as, like throughput, those kind of things. So you need to weigh whether the accuracy, especially like if you look at something like pruning, where you're actually eliminating some of those model weights. And with pruning, there is typically 2 different types of pruning, right? So we're looking at either width pruning. So in that case, we're reducing the weight of the weight matrices. So like removing the attention heads while maintaining the number of layers. So that's width pruning. In the case of depth pruning, we're actually looking at removing entire blocks or layers, but keeping the size of the remaining weights unchanged. But with each of those methods, and there's different methods within there, right? So there's different approaches, and a lot of the approaches focus on width only, or a blend of width and depth pruning. But the thing to keep in mind and the thing that you need to benchmark is whether the accuracy takes a big enough hit where it doesn't make it worth it for you, right? So you need to still look at the accuracy. Although it's going to result in a smaller model, it's going to make it easier for hosting. You do have to make sure that you're benchmarking to make sure you're not taking an accuracy hit that is not okay for your given use case, if you will. So then if we go down, and there is code for all of these in the GitHub repo as well. We don't have code yet for the inference optimization toolkit that was released last week, but we'll get some code out there for some more examples there. Or you can look at the blog for some immediate code examples too. So the next one in terms of reducing model size is post-training quantization. Oh, and I was wrong. Quantization was covered in chapter 4, not 3. But in chapter 4, we covered training quantization. So like Q-LoRa was mentioned. So Q-LoRa is a technique during training to apply quantization during your fine tuning. In this case, we're looking at post-training quantization. So, and you can't do this with every model, right? But with post-training quantization, what we're trying to do is transform the model's weights after training. So in that case, it's still the same goal, right? Where we're essentially looking at, if we look here, we're reducing the model's weights ultimately to try to get a model size that is smaller. So like a 32-bit model quantized down into 8-bit model. So with this, there is, again, it's the same thing where there is potential impact to accuracy or performance. However, I see a lot of traction with quantization because often the performance or the accuracy impact or trade-off is small, and it's smaller. It's enough to justify kind of the reduced model size, the reduced compute that's required to ultimately compute in memory that's used to host this model. All right. But again, you have to benchmark, right? Because there is still potential for accuracy loss. And we mentioned this in the little warning there that you see. Yeah, would the model be as precise? Probably not as precise, right? But you have to measure that against the cost it would take potentially to host the larger model and like the throughput, all the other, I guess, requirements around that, and the loss in precision. While it can affect the accuracy, it may not be as much of an impact and something that you could still tolerate for your existing use case. Then if we go down, so distillation. So distillation, the picture is usually easier to kind of understand there. So distillation isn't necessarily new, right? The idea of having a teacher model essentially be used to fine tune a smaller model is not necessarily new. In this case with distillation, and we are seeing a lot of movement with distillation too, I would say. But basically with that, we're using a larger model, in this case, a large language model, to essentially tune a smaller model that can be used for specific tasks. And the thing to note here is the weights of that teacher model don't change, but ultimately what you're ending up deploying is that student model, right? So the student model is much smaller. And the way that it works is essentially, if you look kind of at the picture here, the teacher model, you have the same data set, right? So you're using training data. And the teacher model is used to predict tokens that are known as soft labels. And then the student models predicted tokens are called soft predictions. So these soft models or soft labels, soft predictions are then used to continue to fine tune through a process of distillation loss. The smaller model, which is then ultimately used for those hard predictions. And the hard predictions is basically just the predictions that are used at runtime. So the one that you actually are deploying to solve your use case or your application. And those are the hard predictions. And then those hard predictions are compared against hard labels, which is ground truth, essentially. And you're calculating loss, right? And using that to continue to fine tune that student model. And again, this one is focused on you only deploy that student model. So that way you have a smaller model with less compute, less memory requirements that ultimately you are using to host your models. There's actually another like step-by-step distillation. Some Google researchers introduced that somewhat recently. That's another compelling way, but they really focus in that case on like utilizing this process for creating those fine-tuning data sets that ultimately then fine-tune a smaller student model. All right, tried to go through that super quick, but mainly just to give you an intro into it. In this one, we talk specifically in this session here about model optimization techniques for inference that are aimed to reduce the size of the model. Like we talked about before, there's other like techniques, post training as well, right? So if we look at like speculative decoding, look at like flash attention, a lot of techniques, a lot of research happening in this space for sure. All right. That being said, I know there's 13 minutes left for Chris, right? And I'll try to answer some of these questions in the chat. I tried to do it as I went, but let me, I'll run through it too.
Cool. Okay, yeah, there's a bunch of questions here.
I think some of them were answered.
Yeah.
Yeah, quantization is different than PCA.
Okay. You can also ask ChatGPT. Funny.
Oh.
All right, let me grab the screen share. And going to see there's code. But before that, I want to do a quick, so I'll be talking about actually, yeah, it's more than just multi-agent optimization. You can pretty much optimize anything with DSPy. Shelby, I'm going to put you on mute there also. Okay. But this does include multi-agent as well, and there are samples. The repo I'll be working out of here is the DSPy repo, and it is DSPy for those of you that joined late, confirmed by the creator of DSPy itself. Hopefully, if you've been saying it wrong, put this in the chat here. Okay, and specifically the examples folder here. Be a lot of where I'll be accessing and believe doing. There's the example. There's an example right at the root of this repo, and I'll zoom in here in a bit. That's the one that I'll be working out of there. Okay, so what is DSPy? Let's appear here. It's a Stanford NLP project. Some of you may remember back in the Spark days, there was a project called Core NLP that came out of Stanford. So Stanford has a long history in natural language processing, natural language understanding. This project actually represents the work that was described in two papers from 2023. And one sort of interesting tidbit, so this person, Omar, is the main person that I've seen that is tied to this repo. He's the one that has, I think, the most webinars out there and the most descriptions. And he's also first on these papers, which is significant. The other thing to notice is there's another person that some of you might know, Matej Zaharia, who comes from Databricks and was one of the original creators of Spark. Now, Matej has some roots or had done some postdoc work at, I believe it was MIT. Then he came back to Stanford. He's out of Berkeley, so he actually does quite a lot of work with Berkeley as well too. That's where Spark came from. So there's quite a lot of folks behind this project here. Some pretty high power folks, Chris Potts, and folks I've been keeping track of for quite a while. So instead of going back through the papers, I'm just going to summarize what they've discussed here. So declarative self-optimizing pipelines for language tasks is sort of the kind of high level description of what this project is. And the way I like to think of it is it's really hyperparameter optimization or hyperparameter tuning for your language pipelines. And what this really starts to represent is a shift from prompt engineering, which is what we've been calling it the last couple of years, into what's now considered more of a flow engineering. Flow engineering is actually a relatively difficult term to Google for because it's used in a lot of different domains and a lot of different contexts. But if you haven't heard of this term flow engineering, this is what all the folks are starting to get into these days. What problems does DSPy solve? So if you've done any of this, modern ChatGPT language stuff, you have certainly had to create your own prompt. And if you're doing anything at scale, you've created what are called prompt templates. And usually these are specific to a given task, the combination of the task, of the data set, and the actual model that you're using, the actual LLM foundation model. And if you've ever tried to go from using OpenAI's GPT-4 to using Bedrock models or the Titan models from Amazon, or if you've gone to try to use Llama 3, or even gone from 2 to 3, from Llama 2 to Llama 3, you likely realize that the prompt template that you were using before is not as optimal as it was with the previous model that you were using. And so what DSPy helps with is that you, instead of manually creating these, you can actually have DSPy generate a bunch of different prompt templates. And prompt template, I have a slide on here in a bit from our book, is the combination of an instruction. For example, answer this question is a simple instruction. And then give it the context, maybe some documents, right? If you're doing RAG, you would pull in a set of documents, and then you would have a question down below. So you would have instruction, you would have the context, and then the actual question, for example. Okay, and the problem here, and so I mentioned the actual evolution of the prompts and managing these prompts as either your task changes slightly or the data set as new data is coming in, or if you want to change. So the other problem here is you potentially have much higher cost if you're not using an optimized prompt, or if you want to change to a cheaper like LLM, say that you want to go from GPT-4, which is relatively expensive, to the newer Anthropic Claude Sonnet, right? And which is a cheaper model. If you do that, the prompt has to completely change. Maybe there's XML involved because Anthropic, for whatever reason, decided to train using XML, and so it's very sensitive to, or it's quite optimized to have XML in the prompt. I'll show examples of this here in a bit. Okay, but real quick, let me make sure I'm covering everything here. Okay, so the fundamentals of DSPy. So declare your tasks, and this is usually done using signatures. So there's inputs and outputs, just like any function signature. There's concept of modules, there's a pipeline, and there's an optimizer, okay? And you provide your data set, you provide the optimization metric that you want for this, quote unquote pipeline of, transformations, queries. And so I think what I was starting to say before was what's different here is you actually, so you tell DSPy what your data set is and what you're trying to optimize, as well as the signature for your task. And I'll show some examples of signatures here in a bit. And DSPy can actually generate all these different combinations of the instruction, of the few shot examples that are passed in, the context, for example, and can even modify it, to use XML or to use something specific to the model that you're trying to use. And so through this optimization process, which if you can hear my M3 laptop here, I have 128 gigs of RAM and on my M3, and this is taking quite a long time. So I'm running a sample in the background. It's very, very compute intensive. You will almost always get a like OpenAI API throttling error if you're trying to run these samples. And so you have to be somewhat thrifty in which models you choose as the judge, that's going to actually do the evaluation for the metric, versus the model that you're using for the reasoning, for generating the prompts, for things like that. So now you might be wondering, just in case, what is a prompt template? So real quick, in context learning, often called ICL, this is really where this prompt engineering stuff comes into play. So if you just take a simple, classify this review and give it the review, and then ask the model to provide you the sentiment for this review, the more samples that you give, yes, oftentimes up to a limit, the better or more likely that this model will get it right. Now, this, of course, depends on the size of your context window, which these days is 2 million, or it's in hundreds of thousands. Some of the original models were 512 tokens, or 4096 tokens. But these days, these context windows are pretty big, and you can pass in a whole bunch of documents or a whole bunch of these samples here, the examples. And so this is actually the quote unquote hyperparameter tuning that's happening. Is DSPy can figure out and can generate better samples and higher quality samples to pass in with your actual like request here, which is, here's a new review that we don't have an answer for, and can you tell us who would use this product, right? And this is obviously negative. Okay, so a prompt template is just extracting this out. Usually at the end of the day, there's some kind of Jinja template, if you're familiar with that Python framework or Python library. And so these are the examples. And so once again, this is what DSPy is going to tune, and also some of these things here as well it can tune. And so here's an example. If you switch over to use Claude 3.5 Sonnet, you can take, or DSPy will actually recognize this and convert this into optimal samples with the review tag, with a like XML review and then sentiment tag, and then come down here and then ask the same question, but modify this separate. Okay, so these are some of the things that happen. It's not easy. If you just take this simple example and pass it into Sonnet, may or may not give you the best results. And so what you want is some framework that can actually find the best prompt and prompt template for you. So how does this optimizer work? And there's been some naming things. So let me just sort of cover this. If you're looking at the DSPy code base, you'll see something called teleprompter. This is actually very confusing, specifically for us Americans, where a teleprompter means something very different. But if you kind of break this word down, it's, tele is from afar, and then prompting. So prompting from afar. They are in the process of renaming teleprompter and the package and all that for the project to use the phrase optimizer. Now, this is actually so similar to how you would optimize basically anything. You have a data set, and that's what you're going to use to train. You have some sort of numerical optimizer. This could be gradient descent. This could be any sort of discrete like optimization function. And then you have your loss function, what you're actually trying to optimize for, right? And this goes through a multi-step process. And this is what DSPy calls compilation, or the like compile phase. I've gotten used to the compile term, but I would have preferred if it was something like optimize, because it just kind of fits better with the sort of rest of the like terminology. All right, so here's some core concepts within DSPy. There's optimizers, like we've talked about a little bit. There's signatures, there's modules, there's your metrics, and then there's retrievers. Now there's a couple more. There's the assertions and some other things here, but I won't have time for that. And But I do want to talk, so here are some of the specific optimizers. Bootstrap few-shot, this is usually if you only have 10 or up to 50 examples that you have to provide to this DSPy optimizer, this pipeline, then you would use Bootstrap few-shot. Now the few-shot is, if I jump back up, few-shot, once again, is give it, find a good number of these examples. Here, we're actually giving 2 examples that are complete, right? With the instruction, with the actual context, which is the review in this case, and then the answer, which is the sentiment, which is positive, negative. And so that's what this few shot here, Bootstrap. So we're sampling from these 50 examples. There's also random search. So this is really where most people start. And this is if you have up to about 300 examples. Now there are more optimized, more recent, and I'll talk about the MiPro here. And this is if you have many more examples. So there's actually 2 optimizations that I'm going to cover here, which is the few shot, which is those few that are passed in, as well as the actual instruction. And so MiPro is designed to actually fine-tune not just the few shot examples, but also the instruction. So maybe we can rephrase the instruction differently. We can break it down into multiple steps. And so this is a common pattern that you'll see with the DSPy project, and specifically the creator Omar talks about this quite a bit, where it used to be, or not used to be, but classic thinking is you could type in this pretty advanced prompt into ChatGPT or into Bedrock and get back your answer. And that's not the case with like some of these more nuanced type of like question answers, let's say, if we're going to focus on the question answer task. And I've seen this personally where I'm trying to find a very specific thing, or I'm trying to find all of the results that are related, but I just get back one little excerpt or one reference that's in a whole bunch of documents. Let's take a RAG example where we're stuffing a whole bunch of documents into the context. And so with DSPy, this can actually break that question into multiple questions. And so that's actually one of the steps in this multi-step phase here. So it can take your single prompt and can actually generate multiple candidate prompts that are similar, that are maybe more specific, and can tune and figure out which of these prompts, which is the instruction plus the few shot examples, is the best combination given the training samples that you've provided. And some of the hyperparameters are, obviously the number of the candidate prompts that it's going to generate. You can tell it, or it will figure out how many of these training samples are needed, during the optimization process. It can also batch certain prompts up and can then present them. So, like again, here's Omar's name, and then Mate are on this as well. So pretty cool stuff. I actually saw a talk by Mate, oh gosh, maybe 3 years ago, and he was hinting at some of this stuff, or maybe it was 2 years ago. And then, suddenly these papers landed in 2023, which was really exciting to see him talk about what his lab was doing, and then finally becoming the actual paper as well as code. Okay, so let's get to some of the, so we had just talked about the optimizers. Now let's talk a little bit about the signatures. So for example, here is a sample signature. This would be, give it a review and arrow sentiment. This is just the syntax that DSPy uses. Just got to kind of get used to it. And here's the actual review. Here's some, so this would be classification. This would be question, arrow, answer. We would have, documents, summary for summarization. For a RAG question answer, you can, instead of just single, a single input, a single output, like question answer and like summarization, you can actually do multiple inputs. You could do multiple outputs. You could do multiple inputs and multiple outputs. This one's particularly interesting because you're asking DSPy to produce the reasoning. And so this is where you want something that is capable of chain of thought reasoning, which gets me into the next section here, which are some of the example modules. So we talked about the optimizers, we talked about signatures. Now let's talk about the modules. The most basic module is the predict module, and you'll see this in pretty much all of like the other modules. At some point, they are using predict. Predict is really the sort of core abstraction here, and it's actually storing what is being learned during the DSPy compilation process, the instructions, the examples, the few shot examples. Some of you might be familiar with the React. This is an agent that can use tools to go out and check the weather, can do things, and can then ultimately implement this given signature. And then our favorite chain of thought, COT, think step by step before fulfilling the signature. And actually, most of the examples that I've been using recently involve the chain of thought. And there's actually one more even cooler, which is multi-chain comparison. So this can actually do multiple chains of thought and then compare the outputs and then produce the final results. There's also program of thought, which can actually perform the code execution to fulfill the signature. And then there's also, so these are all classes in Python. And then there's a few of these. There's one example of a function, which is the majority, which can collect the most popular responses and or can vote on what is the most popular response from a set of predictions. All right, let's talk about the eval metrics here. So some of them that are built in are answer the exact match. And this one you'll see, so this has to exactly answer what was predicted, right? Or the like ground truth. So the ground truth must match. You can build and sort of mix and match your own evaluation metrics. And here's an example here where there's the correctness. There's also faithfulness. So, how correct is this to the actual, what they call golden answer? And then you can also factor in what's called faithfulness, which is how relevant is the answer to the context that was provided, okay? And then there's also, what would be the other one? If it's harmless, so that's something else too. So usually I typically see folks implementing their own metrics. So you would just follow one of these examples here, and at the end of the day, you're just doing some sort of fuzzy match on the text that is the output. And okay, let's talk about the retrievers. So we've got a snowflake retriever, from your like relational store. And let's see what else here. We have the Milvus, and which is what Christy spoke about. Vice, which comes out of Facebook. So these are different vector stores. A project that I've been paying attention to recently is this Ragatuli. So check that out. Probably have some more on that next month when I get into figuring it out and poking around. And real quick, we'll do a quick demo, and then I think we'll have to wrap it up. So this is going to be, is this the multi-hop question answer? So multi-hop, by the way, is that concept of taking the original prompt, breaking it up into multiple, getting answers. So after reading the retrieve results, I can generate extra queries that can then gather more information. And this is something that you probably do on your own when you're using ChatGPT, right? You are out there, you ask a question, it gives you something similar to what you're looking for, but not exactly, and then you start to refine the questions. And so the multi-hop is extremely popular. I see it in lots and lots of use cases, and it is going to collect more and more of this information and then provide the final answer. And this is where things can get pretty costly. And between hitting throttling errors with OpenAI and my laptop that's almost on fire here, I've I've literally never heard this fan go on until today's demo that I started running. And I am using my laptop partially because I hit the throttling exception from OpenAI this morning and I can't seem to recover from it. The hot pot question answer, this is a pretty cool data set here. It's 113,000 question answer pairs from Wikipedia. Answers do require reasoning over multiple supporting documents. So this is forcing the reasoning. The questions are diverse, sentence level support, facts that are required for the reasoning, and it's performing what they call a factoid comparison to test the question answer, this system's ability to extract relevant facts and perform the comparison. So let's see where we're at. I don't think it's done, so I probably, this is the hot pot QA with MePro, which is one of the examples that I showed earlier that I sent a link to. I don't think it's done, but essentially it's let's see, question we're trying to answer, list of potentially related passages, comma separated list of numbers corresponding. And so what you're doing is, so here's the context, question, and then from the question, it is then going to provide, so the first step here is to generate more questions. So I've got the original, question with some context. Let's say we went out and extracted a whole bunch of things from Snowflake or from Databricks or from your like knowledge store. And we're then going to generate more questions, right? Which is a bit counterintuitive, but in practice, this is what you're doing when you're working with ChatGPT, like most likely anyway. Okay, and then we're going to take all that and then generate the answer, and then it's going to rank these documents. So there's some ranking involved here. And let's see, yeah, it's still performing the evaluation. This is what's burning up my drive for the last hour, or my fan for the last hour. Here you'll see the term teleprompter. If you see teleprompter in these samples, which you very likely will right now, just swap in the term optimizer and it'll make sense. The other thing to note too is they do tend to turn the temperature up. So this is pretty high temperature here. And that's because we want to explore and be more dynamic, be more creative in coming up with some of these questions. The ranking will then help to sort of throttle that experimentation back a little bit more into the exploitation phase. Okay, so this one didn't finish, but the other one to look at, this one is a fully generated, so there's nothing that actually needs to be run. It's actually committed. This is from a workshop last year, 2023, DSPy tutorial. It's been updated, so it's in pretty good shape here. Here, you give it some question answer pairs for the training. And let's see, so this is real easy. This is just the basic predict with a question and an answer. Antje will like this. What is the capital of Germany? The answer is Berlin. Very nice. Okay, and here is they're creating a like custom module called COT that is using the built-in what they call submodule, which is chain of thought. So really this is probably, so this is where we're creating one module in our DSPy pipeline. There could be multiple modules that are chained together. And what's going to happen is DSPy is going to find the best prompt and the best prompt template for each module and each submodule that's in our system, which again is why when you do these optimizations, there's so many calls out to the large language model and out to OpenAI. Okay, and here's the metric for answer the exact match. That's why they call it EM. So here's another optimizer here, compile. So that's compiling our module. We're giving it the training data set. We've given it the metric, which is the exact match, and telling it to max bootstrap samples is 2. What is the capital of Germany? Here you see that the rationale, determine the capital of Germany. We know that the capital of Germany from Wikipedia is Berlin. So, relatively easy. And then you can inspect the history. So that's just a basic example of kind of what was happening here. And here's some question answer. So this is physically what's happening under the hood. So the last call to the language model, we could see the prompt and the output. So given the field, so this is the instruction, which was for this particular data set and this particular task was determined to be, and for this particular model was determined to be the best instruction. Here's the context, question, answer, question, answer. So these are the few shot examples. 6, between 5 and 6 typically is a decent number from what I've seen. And then follow the following format. So again, this is something I probably would not have put in my prompt, but this is what DSPy is suggesting, is using, and it's providing the questions, providing the reasoning. Let's think step by step in order to produce the answer. That's the template part of this here, question, and then think step by step in order to determine which author is English, blah, blah, blah. And then what is capital of Germany? Let's think step by step. We know the capital of Germany is Berlin. So very, very simple example, but pretty cool. Now, they start to layer in a little bit more. So here we've got 3 of them out of 13 are correct. That's just straight vanilla chain of thought. Now they're going to add in, so now we're actually going to perform some RAG. And we're actually going to retrieve, add that into the context. We're going to generate some of these search queries against that RAG source. We're then going to, let's see, compile. So this is what they're calling optimizer 2, teleprompter 2. And they're also switching, I believe, to the random search here. I don't think that was used up above. So doing something slightly different. And a little bit more. So the RAG gives us 6 out of 13. So that's not bad. So we got, twice the performance here. And again, here we can inspect what's actually being used. So here we see a little bit different prompt. We also see all of this additional context coming from our RAG source, from our retriever. And we get a little bit better answer. Now, here's the multi-hop. So this is this is separate from RAG. So RAG was up above. Now this is just multi-hop. And so question to the search query, and then it's going to do some of this here for, let's see, what's the result here? I think it was 8 or 9 out of 13. So here we have 61.5%. So we're getting better and better and better. And this is comparing without RAG, with RAG, and multi-hop and non-multi-hop. Okay, so I think there's some examples here. Antje, I think we've run out of time. Any questions I should address? Let's see the bootstrap.
There's a couple of questions in the chat if you want to have a quick look.
Yeah, also I got understanding planning for iteration. Yeah, it's nerve-wracking to know the cost. And one thing that's cool, I think I have this example here. They actually show in a lot of these examples, they dump out the cost, or not like dollar value cost, but they say the number of calls to your source. I don't want to jump around too much because I have OpenAI keys and stuff in here, but yeah, basically it will tell you the particular DSPy compilation that you are about to do is, the number of tasks that you have, the number of times the number of modules, times the number of few shot examples, times the if it's multi-hop, times the number of hops, and so they're pretty conscious about how expensive this is. And yes, so used in line, more used to optimize prompt template. Yeah, so the question here is, like, can I use this on my request response path? Like, can I deploy a DSPy this optimization in production? I certainly would not because of the cost. Think of it like an offline operation, which I think you mentioned here. You described it as that. Think of it like you would run this offline, and then you would save out the pipeline. Okay, I think, yeah, how do you define model parameters, temperature, and all that stuff? Yeah, it's a good question. So if you look at this, temperature, temp. So up there, temperature, where did I see temperature? Yeah, you could set temperature just like you would anywhere. The initialized temperature right there. And I think, yeah, here we were setting it to 1 because we do want it to be creative, setting the number of batches. Yeah, all the API keys, of course, you can pass in. Great. Okay, Antje shared an example. Antje, is that Bedrock example from one of the heroes, or yeah, someone out there? That's awesome.
Yeah, Davide.
Oh, awesome. Okay,
and I think there was a question, the notebooks you're showing, if they are available somewhere.
Let me grab that link. Yeah, so it's just the Stanford NLP examples. There's one right at the root of this DSPy GitHub repo, which is kind of an interesting place for a sample. So you could tell someone was panicked during a workshop and had to just upload it and put it in the easiest place for people to find. So that's the one that's running here. And I think that's it. We're about 20 minutes over. So let's see the cost. Yes, there's a snowflake example. Let me just get that my buddy wrote. Here's a snowflake example. You can, if you don't use Snowflake, don't worry about that. This shows how they chose a cheaper model using DSPy and Snowflake data. So that's a pretty cool demo there. GitHub repo by my buddies at Snowflake. And what they did was they were not sure, if they could get this, or they were manually trying to compare Mistral to Llama, and they were having a really hard time trying to figure out what's the right prompt, because of course Llama has like a wacky prompt with the instruction INST and all that stuff, and then going back to Mistral different. So this was a real world use case. They just so happened to be using Snowflake data. It was for a Snowflake customer, and they decided to use DSPy, and they were able to find which model was the cheapest for this use case. Now, again, you have to remember that this is very, very use case dependent, very data dependent, and they were comparing. So this is Mixtral, so mixture of experts, compared to Llama 370B, which is a relatively expensive in terms of compute resources and memory compared to the Mixtral. And they were able to determine, I believe here, that they determined that Mixtral was 94%, which is 5 times cheaper than Llama 70B. And so, yeah, pretty interesting stuff. A lot of cost savings. Think of it like a one-time hit to, for your specific task, for the specific data set, and for the model. And you can compare the different models. And then at that point, push it out into production, and now you have your faster and cheaper pipeline. So hopefully that helped. We'll see you folks next month. We'll be doing some multimodal and having fun with that. Yeah, Antje, yeah, anything else?
That's it. Thank you.
Just
Yep.
Examples here. I'll post the examples here. Yep.
Some more example questions. Yep.
Okay, I'll post that link here, just the examples. And have a good rest of the day, everyone.